Welcome! In this video, we'll explore an exciting problem from LeetCode, problem number 1392, longest happy prefix. We'll dive into the problem statement, analyze different approaches, and break down the most efficient solution. Let's get started. In this problem, we are working with a string s. A prefix of a string is any substring that starts at the beginning and ends at any position within the string. Similarly, a suffix is any substring that starts at any position within the string and ends at the last character. A happy prefix is a specific type of substring. It is a prefix that is also a suffix, but it cannot be the entire string itself. The goal here is to determine the longest happy prefix for the given string s. If no such prefix exists, we simply return an empty string. The input will always be a string composed of lowercase English letters, with a length between 1 and 100,000 characters. The output should be the longest happy prefix of that string, or an empty string if no happy prefix exists. To understand this better, let's look at some examples. For the string s equals level, the prefixes are l, lu, lev, leave, and level. The suffixes are level, evil, vel, l, and l. Among these, the only prefix that is also a suffix is l. This makes l the longest happy prefix. Similarly, for s equals ababab, the prefixes are a, ub, aba, abab, ababa, and ababab. The suffixes are ababab, babab, abab, bab, ub, and b. Here, the prefix abab is also a suffix, and it is the longest happy prefix in this case. Now, let's take another example. If the string s equals abcd, the prefixes are a, ub, abc, and abcd, while the suffixes are abcd, bcd, cd, and d. In this case, there is no prefix that matches any of the suffixes, so the longest happy prefix doesn't exist, and the output is an empty string. This demonstrates that not all strings will have a happy prefix. Additionally, the constraints of the problem specify that the string length can go up to 100,000 characters and will only contain lowercase English letters. This means that our solution must be efficient enough to handle larger inputs. There are several edge cases to consider. For a single character string like s equals a, there cannot be a happy prefix since a prefix must be shorter than the entire string. The output in this case would be an empty string. For strings with no repeated characters, such as s equals abcd, there are no prefixes that match any suffixes, so the output will also be an empty string. On the other hand, if all the characters in the string are identical, like s equals AAAA, the longest happy prefix would be the string excluding its last character, in this case, AAA. Finally, when dealing with very large strings, the solution must ensure that it operates efficiently within the given constraints to handle inputs close to the maximum length of 100,000 characters. To solve the longest happy prefix problem, we first consider a brute force approach. Here's the idea. Since a happy prefix is both a prefix and a suffix, we iterate through all possible prefix lengths of the string. For each prefix, we check if it matches the corresponding suffix. For example, if we're checking a prefix s, 0i, we'd compare it to the suffix s and I. While this method is intuitive and straightforward, it involves comparing substrings repeatedly, leading to a time complexity of O, n squared. This quadratic runtime is a significant drawback, especially when the input string is very large. On the positive side, this method requires no additional memory since we're not using extra data structures. However, due to its inefficiency, it's not feasible for strings of length up to 100,000, which makes it impractical for competitive programming or large-scale applications. To improve upon the brute force approach, we can use an optimized method based on the Knuth-Morris-Pratt, or KMP, algorithm. This technique pre-computes a structure called the LPS array, which stands for longest prefix, which is also a suffix. The LPS array helps us efficiently track overlapping patterns in the string. Here's how it works. First, we construct the LPS array for the input string. Each entry in the array at position I tells us the length of the longest prefix that is also a suffix for the substring ending at position I. Once the array is constructed, the value in its last cell, LPS N1, gives the length of the longest happy prefix. Using this value, we can directly extract the desired prefix from the string. The beauty of this approach lies in its efficiency. Both the construction of the LPS array and the solution itself run in linear time, or O, n. However, this method does require O(n) space to store the LPS array. Compared to brute force, the KMP-based solution eliminates redundant substring comparisons, making it far more scalable. Additionally, as an alternative, we could consider using hashing, such as the Rabin-Karp technique. By computing hash values for prefixes and suffixes, we can compare them directly instead of the substrings. This approach also achieves a linear runtime but comes with the added complexity of handling hash collisions, which makes it less intuitive to implement. While hashing is a viable option, it lacks the clear structure and alignment with the problem that the LPS array provides. Given the various methods, the KMP algorithm stands out as the preferred choice for solving this problem. Its efficiency is unmatched, reducing the time complexity from O(n) squared in the brute force method to O(n). This makes it well suited for handling large inputs without performance degradation. Compared to hashing, the KMP approach is more elegant and straightforward, as it avoids the need for advanced collision handling. Furthermore, the LPS array directly aligns with the problem's requirements, as it captures the relationship between prefixes and suffixes explicitly. This alignment enhances both the clarity and readability of the solution, making the implementation more intuitive. Overall, the KMP algorithm not only ensures optimal performance but also provides a clean and structured way to solve the problem. For these reasons, it is the most effective and practical strategy for finding the longest happy prefix. Let's continue. Let's continue. Let's continue. Let's continue. Let's continue. Let's continue. This solution leverages the KMP, Knuth-Morris-Pratt, algorithm's preprocessing step to compute the longest prefix-suffix, LPS, array. The LPS array helps us identify the longest prefix, which is also a suffix. First, we initialize the LPS array to store the LPS values for each character in the string. The length variable keeps track of the current length of the matching prefix and suffix. Starting from the second character, index 1, we iterate through the string, comparing current characters with the character at the length index. If characters match, we increment length and update the LPS array for the current index. If they do not match and length is greater than 0, we fall back to the previous LPS value, allowing us to retry with a shorter prefix. Once the loop completes, the value in the last index of the LPS array gives us the length of the longest happy prefix. Using this value, we slice the input string from the start to this length to return the result. This approach ensures efficiency with a time complexity of O(n), where n is the length of the string. It processes the string in a single pass while using constant space for variables other than the LPS array. This is the Java implementation of the LeetCode problem number 1392, longest happy prefix. The solution mirrors the logic of the Python implementation by using the KMP, Knuth-Morris-Pratt, algorithm to compute the longest prefix-suffix, LPS, array. Key differences include type declarations for variables, Java's substring method for slicing strings, and the use of Java's zero-based indexing. The LPS array is used to determine the length of the prefix that is also a suffix, and the result is returned as the substring of the input string. We begin by examining the input string level. First, we initialize our variables. The length of the string, n, is 5. We create the longest prefix-suffix array, or LPS array, initialized to 0, 0, 0, 0, 0. This array helps us track the length of the longest prefix that is also a suffix as we iterate through the string. Additionally, we set the variable length to 0, which will be used to track the current prefix-suffix match length. Now, to build the LPS array, we start comparing characters. For I equals 1, we compare S1, which is E, with S length, which is S0, or L. There's no match, so length remains 0, and we update LPS 1 to 0. The LPS array remains 0, 0, 0, 0, 0. Next, for I equals 2, S2, which is V, is compared with S0, which is still L. Again, there's no match, so length remains 0, and LPS 2 is updated to 0. The LPS array is still unchanged. For I equals 3, we compare S3, or E, with S0, which is L. Once more, there's no match, so length stays 0, and LPS 3 is updated to 0. The LPS array remains 0, 0, 0, 0, 0. Finally, for I equals 4 each S4, which is L, is compared with S0, which is also L. Here, we have a match between S4 and S0. As a result, we increment length to 1, and LPS4 is updated to 1. The LPS array now becomes 0, 0, 0, 0, 1. At this point, we proceed to extract the longest happy prefix from the string. The last value in the LPS array, which is 1, tells us the length of the longest prefix that is also a suffix. Using this, we can return the first character of the string, S1, which is L. This is the final output for this example, L. Now, we examine the input string ababab. Once again, we start by initializing our variables. The length of the string, n, is 6. The LPS array is created as 0, 0, 0, 0, 0, 0, and length is set to 0. To build the LPS array, we begin comparing characters. For I equals 1, we compare S1 or B with S length, which is S0 or A. There's no match, so length remains 0, and LPS1 is updated to 0. The LPS array is 0, 0, 0, 0, 0, 0. Next, for I equals 2, S2, or, is compared with S0, which is also A. This time, we have a match, so we increment length to 1, and LPS2 is updated to 1. The LPS array becomes 0, 0, 1, 0, 0, 0. For I equals 3, S3, which is B, is compared with S1, which is also B. Once again, we have a match, so length is increment to 2, and LPS3 is updated to 2. The LPS array updates to 0, 0, 1, 2, 0, 0. Finally, for I equals 4, we compare S4, or A, with S2, which is also A. Here, we observe another match between S4 and S2. This causes length to increment to 3, and LPS4 is updated to 3. The LPS array now becomes 0, 0, 1, 2, 3, 0. Next, for I equals 5, we compare S5, which is B, with S3, which is also B. This is yet another match, so length is increment to 4, and LPS5 is updated to 4. The final LPS array is 0, 0, 1, 2, 3, 4. To extract the longest happy prefix, we refer to the last value in the LPS array, which is 4. This tells us the length of the prefix that is also a suffix. Using this length, we return the first 4 characters of the string, S4, which is ABAB. This is the final output for this example, ABAB. For the final example, the input string is AAAAA. As always, we start by initializing our variables. The length of the string, n, is 5. The LPS array is initialized to 0, 0, 0, 0, 0, and length is set to 0. Moving on to build the LPS array, we start with I equals 1. Here, we compare S1, which is A, with S length, which is S0, also A. Since there's a match, we increment length to 1, and LPS1 is updated to 1. The LPS array becomes 0, 1, 0, 0, 0. For I equals 2, we compare S2, or A, with S1, which is also A. Again, there's a match, so length is increment to 2, and LPS2 is updated to 2. The LPS array updates to 0, 1, 2, 0, 0. Next, for I equals 3, S3, which is A, is compared with S2, which is also A. Here, we find another match between S3 and S2. This increments length to 3, and LPS3 is updated to 3. The LPS array now becomes 0, 1, 2, 3, 0. Finally, for I equals 4, we compare S4, which is A, with S3, which is also A. Once again, there's a match, so length is increment to 4, and LPS4 is updated to 4. The final LPS array is 0, 1, 2, 3, 4. To extract the longest happy prefix, we look at the last value in the LPS array, which is 4. This indicates the length of the prefix that is also a suffix. Using this, we return the first 4 characters of the string, S4, which is AAAA. This is the final output for this example, AAAA. The time complexity of this solution revolves around the Knuth-Morris-Pratt, or KMP, algorithm, which is used to construct the longest prefix-suffix, or LPS, array. Let's break this down step by step. First, while building the LPS array, the algorithm iterates through the string from index 1 to n1, where n is the total length of the string. This gives us a base time cost of O, n. Inside this loop, there's a while condition that manages the fallback mechanism when characters don't match. However, because of the way the LPS array is designed, the length pointer always moves backward and never revisits already processed positions. This ensures that each character in the string is handled only once, resulting in an amortized cost of O, n, for all while operations. When we combine these details, the entire process of constructing the LPS array has an overall time complexity of O, n. Once the LPS array is ready, the algorithm retrieves the result by slicing the string using the value at the last index of the LPS array. This operation is O, k, where k is the length of the resulting substring. Since k is always less than or equal to n, this operation is also O, n, in the worst case. Therefore, the total time complexity of the solution is dominated by the LPS array construction, making it O, n. The overall time complexity of the solution, as discussed, is O, n, driven primarily by the LPS array construction. Now, let's discuss space complexity. The algorithm creates an LPS array of size n, which requires O, n, space. Apart from this array, the algorithm uses a few auxiliary variables, such as the length pointer and loop counters, which need only constant space, or O1. This means the total space complexity is dominated by the LPS array, resulting in O, n, overall space complexity. To put this in perspective, consider the brute force approach, where we compare every possible prefix with every possible suffix of the string. For a string of length n, this approach evaluates n1 prefixes, with each prefix requiring up to O, n, character comparisons. As a result, the brute force method has a time complexity of O, n squared, which is significantly slower. In contrast, the KMP algorithm avoids redundant comparisons using the LPS array, reducing the time complexity to O, n. This optimization makes the KMP-based solution far more efficient, particularly for large input sizes. Let's now consider the time complexity across different scenarios. In the best case, the string has no repeating patterns, so the while loop is rarely triggered. Even in this case, the complexity remains O, n. For the average case, where the string has some repeating patterns, the while loop may be entered occasionally. However, the amortized time complexity still holds at O, n. In the worst case, if the string contains extensive repeating patterns, the while loop is entered more frequently. Yet, because of the non-overlapping nature of the LPS array construction, each character is processed at most once, and the complexity remains O, n. To mathematically justify this, every character in the string is either directly compared through the if condition or skipped during a fallback via length equals LPS, length 1. Since no character is revisited, the total operations are proportional to the string length. This guarantees an overall time complexity of O, n, regardless of the input pattern. When solving the longest happy prefix problem, there are some common mistakes to watch out for. First, ignoring edge cases can lead to runtime errors or incorrect outputs. For example, you must consider cases like empty strings, single character strings, or when no prefix matches the suffix. Skipping these tests can cause your solution to fail unexpectedly. Another frequent mistake is incorrect string slicing. Miscalculating indices when extracting prefixes or suffixes can lead to off-by-one errors, which result in mismatched comparisons and faulty outputs. It's also crucial to optimize for constraints, especially for large strings where n exceeds 10 to the power of 5. Brute force approaches, with their O, n squared, complexity, often time out for such inputs. Finally, assuming symmetry between prefixes and suffixes is another pitfall. Just because a prefix matches a suffix doesn't mean the reverse is true, particularly for asymmetric strings. This assumption can lead to logical errors in your implementation. Additionally, poor hashing implementation can be a significant issue, especially if you're using hashing to optimize comparisons. An inefficient hash function or failure to handle collisions properly can result in false positives or missed matches, compromising the correctness of your solution. Now, when you're tackling this problem in an interview, there are some key insights to keep in mind. Recognizing patterns is incredibly important. String problems often involve prefix, suffix, or substring matching, and knowing when to apply techniques like sliding windows, hashing, or dynamic programming can save time. For the longest happy prefix, the KMP algorithm is an optimal choice, reducing time complexity to O(n) by efficiently finding the longest prefix that's also a suffix. In interviews, it's vital to clearly communicate your thought process. Start with a brute force explanation and then optimize step by step. Interviewers value clarity more than jumping straight to the optimal solution. Finally, don't forget to discuss trade-offs, such as the space versus time considerations. For example, while KMP is faster, it requires pre-processing, whereas brute force is simpler but slower. To deepen your understanding, there are related problems that you might find helpful. For example, LeetCode 28, which asks you to find the index of the first occurrence in a string, or LeetCode 139, which focuses on word breaks, both involve similar string manipulation techniques. Other examples include LeetCode 214, which deals with finding the shortest palindrome, and LeetCode 459, which looks at repeated substring patterns. Exploring these problems can help you recognize patterns and apply the right algorithms more effectively. Now, let's consider the different approaches to solving the longest happy prefix problem. A brute force solution involves directly comparing prefixes and suffixes. While straightforward to implement, it's O(n²), complexity makes it impractical for large strings. On the other hand, the KMP algorithm builds a partial match table, or LPS array, to find the longest prefix-suffix efficiently in O(n) time. This approach is faster, but it requires additional pre-processing and a solid understanding of how the LPS table works. Another viable approach is hashing, which uses rolling hashes to compare strings in constant time. The pre-processing step can be completed in O(n), while each comparison is O(1). However, this method comes with its own trade-offs. The main risk is hash collisions, which can lead to incorrect results if not handled carefully. Ensuring a robust implementation is key to avoiding such pitfalls. Hashing is particularly useful when you need an efficient and scalable solution, but it requires careful attention to detail, especially in choosing and implementing the hash function. To wrap up, we reviewed the longest happy prefix problem and discussed key insights into solving it efficiently. Remember the importance of the KMP algorithm for string matching tasks and leveraging its power in interview scenarios. Thank you for joining me today, and don't forget to like, share, and subscribe for more content. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!